Okay, so yeah, there's two types of forces, um, tension and shear. So tension, um, this kind of relies on um, holding together all the components when it's fastened together. And basically what this does is it transfers load through the joint. As in, like, if you have a force here, it kind of transfers it straight through like that. Um, and shear, it's essentially shearing forces on the bolt, and it kind of relies on the shear strength of the bolt, which is sometimes given to you when looking at spec sheets. And also, let me know if you guys have any questions or need any clarification. So that's that for that. And fastening theory. So essentially, as torque increases, as you increase the torque on a bolt, the bolt starts to resist, resist moment-wise, and it begins to act as a stiff spring, creating a clamp force. So um, if you guys didn't know, if you kind of keep tightening a bolt, it essentially turns into a really, really, really strong spring. And you'll see that in the next slide. Um, and a little kind of termination. There's two types of loads, preload and clamp load. So when people say they're referring to the preload, it's the bolt's tensile load, and clamp load is the bolt's compressive load. So it's two different types of loads. And little fun fact, it's still not widely understood how a bolted joint carries a direct load, which is kind of weird. I don't kind of understand why that is, but yeah. So how to read bolt sizing. So quick question for you guys. Do you guys know how to read this?
Is it the diameter and then the amount of threads after?
Yes. And then what's the last one?
The number of threads? I mean the threading.
The thread count, right?
Okay.
TPI?
TPI is for the second or the third one?
The third one, right?
No.
Oh, well, it wouldn't make sense, yeah. But okay, yeah, sorry, the second one.
Okay, yeah, I just wanted to test you
Because
guys.
if it's per inch, yeah, it's not gonna make sense.
Yeah. Yeah, so essentially, you guys are right. It's the diameter, then the TPI, and then the length of the bolt. So this is kind of useful because when you get your internships or jobs, sometimes you'll be working with bolts, and people will be asking you, do we have any M3 bolts, something like that. And then some people don't know what it is, and they'll get confused, but this is essentially how to read a bolt. And okay, and then more on fastening theory. So whenever you see a graph like this, I'm pretty sure you guys seen this before. It's the stress strain graph. Usually you just see it on materials, but this can be applied to bolts as well. So essentially, we want to stay within the elastic region here, which is before the yield point, around 85 to 90% of the yield strength. And so this is also known as the proof load. So we never want to use the yield point for bolts. It's always going to be below So like this picture on the right, you'll see like this is the yield point. And we want to stay within this elastic region. So this elastic region is why it's kind of considered as a spring, because it can always deform back to its original length. And you can think of this as your new yield point when you're working with bolts. So typically, like when you pass this yield point, for example, you'll reach plastic deformation until you reach the ultimate tensile strength, which is your strongest point, and then failure at the fracture point. So typically you don't want to pass the proof load. In certain cases, I would say you can, but you're kind of getting to that dangerous point where it's going to plastically deform. You just want to stay within this elastic range. Any questions? That was pretty straightforward, right?
Yeah. You
Yep.
should have been my material science teacher.
Wow. So
There
yeah,
should be more of strengths, wouldn't it?
I guess it would be strengths, but yeah. So this is going to be your proof load. And then your typical clamp load is going to be just a bit below that, around 70%, 75% of your proof load. And we'll get into that later. So when you're tightening bolts, there are going to be 4 different phases. So phase 1 is called the rundown, which means that there's no contact between the components. Right? You're putting the bolt together, it's super loose. So nothing is tightened at all. Phase 2 is called the drawdown, which means that it's the point where every component is touching. And then we have phase 3, elastic deformation. So this is where you apply the torque on the bolt and the preload increases, right? You start going up this graph here, start going up and up and up until you want to reach the clamp load. And then phase 4 is the plastic deformation. So this happens when you pass your yield strength and your bolt starts stretching like crazy and starts deforming, and it won't go back to your normal deformation. Right, so there's that. Bearing surface. So what this is it's the area of contact between 2 objects. So for this case, it's essentially your fastener and your bolt area. And you can increase this bearing surface with washers so that the force is distributed to a wider area. So that's why sometimes you would want to use washers because it kind of distributes that load over a greater area, and it kind of reduces your sinking, your sinking, what's called where it sinks, because sometimes if you notice, sometimes when you clamping it down, it starts to sink into the material, right? But since we don't want that, you would add a washer, and then it wouldn't do that. And it also reduces looseness, and it creates a tighter fit. Yeah, and then also sometimes you kind of need to add a distance between the surface and the bolt. So those are what washers are used for. Okay, and next is the friction factor. So fun fact, when you tighten a bolt, you guys notice that there's it kind of pushes back on you, right? So not 100% of that force is going into the material. So when you tighten that bolt together, over 90% of the friction is spent overcoming the surfaces of the joint. And you can see on the picture on the right, so this surface here takes around 50% of that torque, and the nut here takes 40%. And that rest goes into the clamping force or the clamp load. So to kind of think about this is, if you're tightening a really rusty bolt, it's like super hard to tighten together, right? And you're just trying to overcome that high friction factor. And so sometimes when you try to tighten it, it doesn't tighten all the way. And that's where all your torque is going. It's just kind of overcoming those surfaces. And we don't really want that. We want to transfer the most force to the clamp load. And there's some ways that we can kind of overcome that. So some of these include tighter tolerances. So if you have like a really tight tolerance on your bolts and your die, you'll get like a more of a force transfer to the clamp load. Next is alignment. So sometimes when you put a bolt at an angle, it doesn't really, it's kind of hard to put in sometimes. And that's just unnecessary rubbing because it's not aligned perfectly, if that makes sense. And then next is surface finish. So we have something like, if you think about polished surfaces versus a brushed surface, having a polished surface, it's gonna have having a brushed surface, you're gonna have a higher friction coefficient than a polished surface, if that makes sense. So that's why sometimes finishes kind of matter, and you can find these on the spec sheet of a bolt you want to look up, for example. And then we have material type. So we have rigid versus soft materials. Having a more rigid material is actually better because soft materials, they kind of deform easily, and we kind of don't want that. And then lastly, you can use lubricant to kind of decrease that surface friction factor. And so, yeah, essentially you just want the least amount of friction on the surfaces so that we can transfer most of that force to that clamp load. Does anyone have any questions? I know that was kind of a lot. Okay. And okay, so moving on to thread dimensions. So I think everyone knows what this is, threads per inch, so TPI. TPI is equal to 1 over P, where P is the distance between the threads. So that's how you would calculate the TPI if they don't give it to you on the spec sheet. Most of the time they'll just give it to you and then you can just use that, but this equation is just used for finding the TPI. And then there's also another factor, which I haven't really seen before, but it's called the fundamental triangle H. And what this is when you look at a screw, you see how sometimes they cut off the ends to make it flat for the top and bottom portion, but the fundamental triangle is this whole shape here. So it would actually go further up here and further down here. Yeah, and that's calculated with square root of 3 over 2 times p. I don't think this is really important. I just kind of want to let you guys know about this. Okay, and I think here, this is where we're going to start kind of determining the torque on the bolt. So first, we got to start with the tensile stress area. And this is where the stress is applied on a threaded fastener. So if you look on the figure on the right here, this red portion, this is where the stress is going to be applied. So different bolts have different threaded length. Sometimes it covers the whole entire bolt, sometimes it doesn't, but this area is where the stress is going to be applied. And it's also known as the weakest point of the bolt. And so we can use this formula here. A is equal to pi over 4, dn minus 0.9743 divided by n to the fourth. Where A is the tensile stress area, dn is the nominal bolt diameter, which you can find on the spec sheet, and n is going to be your TPI. The 0.9743 is given in the formula itself. Yeah, no problem, Nelson. Yeah, so this is already a given on the formula. And so once you have A, you can use this on your next equation, which is your preload force. So using this equation, you can find your preload force, which is equal to ST times AS times your percent yield. So ST is the yield strength of the bolt, which is why sometimes all of these parameters are based on what type of bolt you use. So you can find the yield strength with the material that it's used with. AS is going to be your tensile stress area, which we found in the previous slide. And percent yield is the preload percent of yield, which basically just means that this is kind of determined on how much stress you want to use. And luckily for us, it's already predetermined. So Shigley, if you haven't heard this name before, you'll hear it in machine design. Shigley recommends 0.64 for non-permanent joints, which just means that if you use fasteners, it's non-permanent. So 0.64 is going to be your percent yield, and recommends 0.77 for permanent joints, which we're not using at all. So just have to worry about this 0.64. Any questions so far? Okay, and so this is our second formula, and then we have one more. So last, we can use, so this is the torque to find the preload. And so we have this formula here, T is equal to KT times D nominal times FPL, where KT is the torque coefficient. So this K is kind of dependent on the surface of the bolt. So there's a lot of sites that already give you this K coefficient. So for example, like if our bolt has zinc plated, we would just use 0.02 for our K. If it's lubricated, 0.18. So we want to get this as low as possible. Denom is the nominal bolt diameter, and FPL is the bolt preload force, which we found in the previous slide. So since this is already given, our K, if you want a more accurate value, you can use this equation below, which I would recommend doing after just using your K, so you can kind of compare. But you can go to the website here to determine the variables. And yeah, that's pretty much it. So yeah, that was the last slide. Does anyone have any questions?
No.
Was it straightforward? Was it kind of like
Yeah.
a lot? So yeah, there's actually a lot more on bolt preload. So I might spend another week on this, but yeah, like there's a lot of stuff that I left out, such as bolt stiffness and clamping force. But I think within the slides here, we can just determine how much torque we need to put on the bolt for now. Yeah, this is like the general idea to start bolt preload. Yeah, so I hope this is helpful for you guys. I know there's a lot of kind of like random slides that are related to bolts, but I just want to get you guys introduced to these topics, so that if I do another slide, you'll kind of get more familiar with it. Because I know I just introduced like bearing surface and like friction factor, but once we go more in depth of it, you'll kind of see these topics pop up. But I think for now we could just stick with these three formulas, starting from tensile stress area, and then preload force, and then torque. So yeah, does that kind of make sense?
Yeah.
Okay. So I think that's that for this presentation. I actually have a question for you guys that are here today. Is there any topics that you want me to present on that will kind of help your sub team?
Not that I can think of. I think hot dog water isn't here anymore either. So
That's okay. Yeah, because I'm planning to maybe start on, let's see, maybe like differential drive or maybe vehicle dynamics. Yeah. So I guess this question is for the people who are in bolt joint analysis. Was this kind of helpful to you guys?
Yeah, I think it was pretty helpful.
Okay. All right. Awesome. Yeah. So I think for now we can get started on meeting with each sub team. So who's here today? Joseph, Gio, Eric, Austin. Okay. I guess, does anyone want to go first today?
I'll go first.
Okay. Gio's team. So, is this for camera stabilization or
Oh wait. You said to present or to meet up?
to meet up?
Frame and bolt preload,
Frame.
frame analysis and bolt joint analysis.
Okay. And then next, I guess, Eric or Joseph. Or Joseph, do you want to join today, or are you just going to be here for the presentation?
For the camera stabilization.
Yeah.
What time is that?
So I'm gonna spend 20 minutes on each team.
Yeah.
So I guess it just depends on what order you go in.
Yeah, I'll be there for that.
Okay, so I'll actually put you last. If that's cool with you.
Oh yeah, definitely. I'll be here all day, so I'll be studying some strength. So
Yeah. And Eric, I know you have work. So do you
I don't know if it's possible to go first, just so it's not rushed towards the end.
yeah, is it okay if Eric's team goes first?
Yeah.
Okay.
Actually, Tim, you
Yeah.
know how I messaged you earlier saying that basically like the tasks that were due this week, I'm gonna be doing this week. So
Mhm.
do we have to meet up since I kind of already know what I'm supposed to do?
Yeah, we can work on it together. I just want to be able to work with you guys, even though if you haven't gotten it done yet, if that's
Okay.
cool with you.
For sure.
Okay, yeah. So then, let's see, solid modeling. Okay, so we're gonna go from Eric's team, which is the solid modeling team, and then frame, and then bolts, and then camera. Is that cool with you guys?
yeah, that's cool. It's cool with me.
All right, cool. So, yeah, I guess then if nobody has any other questions, then we can go ahead and get started on the on the sub teams.